Hello, welcome to the PCCA podcast, Pacific Coastal Computing Association. We're going to start a podcast series where we look at a variety of computational topics, but they'll spread over some of the application domain areas that we want to investigate and bring you on in that investigation with us. I'm Derek Jacoby, your host. I'm a director at PCCA and am a PhD research manager at the University of Victoria. I also run the Victoria Makerspace and am a global teaching assistant in the How to Grow Almost Anything class out of MIT Harvard. And in all of these domains, I really like to intermix a variety of different computational topics. We're going to this morning be watching, for instance, a artificial intelligence talk. But let me first give my co-host Piyush an opportunity to introduce himself.
Hey everyone, my name is Piyush Acharya, and I'm a high school student from Bellevue, Washington. I've been working with Derek for around 3 years now. We actually first got our first paper in on epigenetics relating to ME/CFS and long COVID. I lead my school's programming club. I also organize Washington State's largest high school hackathon. And I also co-founded DNA Analyzer, which is a GitHub #1 trending platform for DNA analysis.
Great, thanks, Piyush. So what we're going to watch this morning is one of the first talks from the 2025 Artificial General Intelligence Conference being held in Reykjavik, Iceland. It started about 1 a.m. this morning, so we're catching up with the live stream recording here later on Sunday morning. We're going to be watching Ben Goertzel talk about Hyperon, an architecture for near-term neural symbolic evolutionary AGI. This should be a fairly high-level abstract talk on what the Hyperon system is. And so we'll probably be stopping a number of places in here as Ben talks to kind of pick apart some of the ideas that he is discussing and making sure that we're really understanding what he's saying. Any thoughts from your side, Piyush, before I launch into the video?
No, super excited. Let's do this.
What we're talking about here is Hyperon, which has grown out of the OpenCog AGI platform architecture and project, which itself grew out of Novometic Cognition Engine, which itself grew out of the WebMind Cognition Engine from the late 90s. So this is the latest in a series of architectures attempting to create AGI by combining different learning and reasoning paradigms within a shared cognitive architecture that then learns from experience, both supervised and unsupervised, and self-modifies to improve itself as it grows. So the philosophy underlying Hyperon and its predecessors was fairly simple at core. I mean, you're looking at a mind as a complex, self-organizing system, which is recognizing patterns in itself, recognizing patterns in the world, among other kinds of patterns, recognizing patterns in which of its actions lead to this results. And you're looking at a mind as an open-ended intelligent system, which is trying to maintain its boundaries and its integrity, while also self-transforming and improving itself to bring itself to new states that it couldn't have previously even understood. And you're trying to do this via whatever means will work, basically. So the high-level cognitive architectures I've been using in this series of systems have been roughly modeled on the high-level cognitive architecture of the human mind, meaning you have episodic memory, you have declarative memory, you have procedural memory, you have working memory. You're perceiving things, you're issuing actions, and you're trying to, among other things, choose procedures that will help you achieve certain goals in certain contexts. There's also a certain amount of sort of ambient self-organizing activity going on that isn't oriented toward explicit goal achievement. But while high-level cognitive architecture that we're looking at in Hyperon is roughly inspired by the human mind, we're not trying to copy exactly what the human brain does, partly because we don't know a lot of what the human brain does, partly because the hardware infrastructure that we have on hand is very different than the wetware infrastructure in the human brain. So we've taken a cognitive architecture roughly inspired by human cognition, and then the different core aspects of learning, reasoning, and memory are filled in with a diversity of different data structures and algorithms coming from cognitive psychology, from computer science, from the traditional AI field, from mathematics. And then we're integrating these things together within a sort of meta representational fabric and operational system that lets different sorts of algorithms and data structures all cooperate, right? So what this boils down to in practice, we have the Hyperon software framework, which I'll describe loosely in a moment and we'll hear more about shortly. Then we have, on top of that, one could build many things. There's a specific cognitive architecture called Primus, which in honor of which we have Optimus Prime here, right, in front of the room, right? And then who's, I mean, highly ethical AGI system, Optimus Prime. I mean, he's kind of cloying, to be honest. I'm hoping we can get a more winning personality somehow. But I mean, as a start, he wouldn't be terrible. At least he's funky, right? I mean, Primus is cooler than Optimus. Primus can turn into a planet. Optimus just turns into a truck, right? But I mean, we could expand in multiple directions. You know? The Primus cognitive architecture is a cognitive architecture aiming human level AGI built on top of the Hyperon infrastructure. And we'll hear a bit about both during these next couple hours. So the Hyperon infrastructure is more new than the Primus architecture because my cognitive architecture ideas have evolved over the years, whereas my thinking about how to build an efficient infrastructure to realize these has changed much more greatly, just as the hardware has evolved and associated tooling has evolved. So regarding the Hyperon software layer, before we get to the cognitive architecture layer, Hyperon software layer, the key element is what's known as the Atomspace, which is a weighted label type metagraph. So it's nodes and links. The links can point to multiple nodes, the links can point to subgraphs. Nodes and links can be labeled with various weights and types. Types themselves are chunks of the same metagraph. And this is intended not to be a commitment to a particular low-level knowledge representation, but rather as a rich sort of meta-representational framework that can be used to implement a neural net, could be used to implement different logic systems, could be used to implement different sorts of programming languages. So you have a flexible representation fabric. And then we have a programming language called Meta, M-E-T-T-A. And we announced a language called Meta a few years ago. Then like 2 months later, Facebook changed their company name to Meta. So then we created a crypto project called the Artificial Superintelligence Alliance. And now like a year later, Facebook has launched a superintelligence lab, right? So I'm starting to think of how I can game this trend somehow. Or pick a really stupid name and see if they'll go for it. Right?
let's pause there for a second and unpack some of the pieces that Ben's been talking about. I think the things I want to comment on in here are, first of all, the evolution of this type of architecture and using artificial intelligence systems to model human cognitive processes. And then we can talk just a little bit about the graph structure that he's proposing for Hyperon here, which really is a knowledge graph at its base, which gives interesting ties into some of the other pieces we'll talk about on this channel. How much do you know, Piyush, about kind of the history of the interrelation between cognitive psychology and AI?
I mean, like on a high level, I know that like we have tried to model neural networks after the human mind, right? But although we have done so in a pretty good way, it's still like a long way away from like modeling the human mind well. And again, that's due to two reasons, like the speaker mentioned. One is that we don't really like have the biological understanding of the human mind to be able to do that. And the second is like the hardware that these systems run on does not really match the human brain. And so because of those two, we've really like failed to model the human mind in a good way.
Yeah, it's interesting. Back in the mid 80s, there was a kind of early attempt at this. Rumelhart and McClelland published a interesting set of connectionist papers that were positing neural networks being used as modeling processes for human cognition. And it really was way too early, that the technology really wasn't there to do a faithful representation of human cognition, but it sparked a whole lot of interesting discussions. And that's kind of what Geoffrey Hinton, years and years later, picked up into that line of research as he did all the seminal work on deep learning. And so, in some sense, that early attempts to model the human mind through connectionist architectures led directly to the deep learning and underlying computing technologies for AI today. But it did so in a way that somewhere along that path lost even the goal of trying to directly model human cognition. And when you look at deep learning systems today, for the most part, they may have this passing nod to working the way that the brain works, but it's really a separate set of processes. And so what Ben's talking about in here is kind of returning back to those roots of thinking about computation as being a set of specialized affordances that are kind of the way that the human brain works, is not kind of this bottom-up organization and this logical construct. It's evolution pushing different parts of the brain to evolve in different ways to form different specialized computation facilities. So I think some of the core of Ben's ideas are this a concept of where you're never going to have one model that does everything. You're going to layer on specialized computation capabilities in a structure that together can do everything. And that was kind of the root of some of the open cog pieces that he was referring to in there that Hyperon has been an outgrowth of.
Yeah, I mean, like even like as I start learning like more machine learning algorithms like XGBoost and random forest, so I was learning a lot about machine learning last summer, and right before our project, and I noticed like while reading Wikipedia pages is that all of those algorithms came out in the 80s and 90s, which was very interesting. And then I watched some talks, and it seems like we were only like just able to use machine learning, all of those algorithms like post 2010 or 2015 when GPUs and hardware got powerful enough.
Yeah, totally. It's been this interesting evolution. Moore's law does a lot of good for the world, doesn't it?
Yeah. Yeah, another thing I wanted to talk about here was memory. I think you had a lot of points here. Do you have anything to talk about there?
Yeah, so this gets into the knowledge graph on the representation of memory pieces, and have a lot going on in my head about that. But I think we're probably going to get Ben going into more detail there in just a minute. The key thing I think is that a project you'll hear a lot about on this podcast channel it involves knowledge graphs in a very specialized way. And what Ben is trying to do here is use knowledge graphs as this a large underlying general purpose architecture for his memory systems, and have a lot going for them. The fundamental concept of memory as it exists in a lot of the LLMs today is not as segregated as a graph gives you the ability to do. You just kind of have this flat context window, and everything in that context window is equally valued. Whereas the real affordance of a graph-based memory structure, like Ben's talking about, is specificity. And if you have a path through the graph, you've got a very specific path through memory. And that just intuitively feels a lot more like the way human memory works. So where you don't remember everything at once equally, you remember a specific set of things occasioned by other memories.
Yeah, that's very interesting because and I'm happy that you brought up LLMs today, because even with let's take ChatGPT as an example, because it's something that most consumers are familiar with. So first, like I think last year they implemented memory, but they implemented it in a not very memory-like way. And what I mean by that is when you told it to remember something, or if it thought something was worth remembering, it simply added it to a list, and then appended it to the context every single time. And now they've added a sort of memory 2.0 feature in the last couple months, where it's able to reference other chats, but like you said, it's not able to weight them based on like how important something is, or yeah, or something like that. And so even with O3 Pro, or today with GPT-5 Pro, they're still not able to access memory in a way that's natural. And I guess like this is one of those problems that perhaps Hyperon is going to fix.
Yeah, maybe. Let's pop back in
Yeah.
and let Ben talk about it.
So yeah, when you see the artificial shithead intelligence, it's just to see if Mark Zuckerberg copies me. But yeah, the meta language, METTA, not meta, although it is meta, but that's a different, but not that meta. The meta programming language originated basically with the idea that we want a language which consists of metagraph rewrite rules, which are then embedded in the metagraph. So chunks of the Atomspace metagraph can be sort of activated and then used to rewrite chunks of metagraph into other chunks of metagraph. And at that level of abstraction, it could be a bit like replicode, which we talked about in the 2012 AGI summer school in this building, Chris and Thorson and co, which was in the era cognitive architecture. I mean, the replicode is also a language of rewrite rules and rewrite rules to get new rewrite rules. Now, digging into the details, we've done a bunch of, I think, more sophisticated functional and logic programming stuff in the meta language. And in terms of the implementation of the meta language, a lot of work has gone on in the last few years aimed at getting that to really work nicely. And you could already see some of the issues confronted there looking at replicode. Like in 2012, there was a really fast replicode compiler written in C or C+, C with little C++, and it was very fast. Only one person understood it. It was super hard to modify or work with in many ways that I wanted to. Then I think a guy named Martin Sandsmark tried to rewrite it to be more elegant, but then that wasn't as fast. So we already had there some of the dilemmas we've been wrestling with meta, which is we want a really, really performant underpinning, but we also want an underpinning which we can evolve over time as AI advances, and which ultimately the AI itself will be able to evolve over time. And so we've spent a lot of time on that in the last couple of years and made a lot of progress. We don't yet have a really fast fully general meta compiler, we seem to be probably within like a month or 6 weeks or something of having that, which is quite interesting. And I think due to the work of Greg Meredith and Adam Vandervoort who's here in the room, and Luke Peterson and a number of others, we have something called the meta optimal reduction kernel, which is a really fast atom space. So it uses some funky zipper machines built over prefix trees as well in Rust to make it really fast for pattern matching and many sorts of unification queries on an atom space. So that's sort of the heavy lifting. And so we're now mostly through the job of making a fast meta interpreter that backends mostly on this more fast atom space. And part of what we'll talk about today, though, is some of the core cognitive algorithms we're interested in, how to implement them in a way that's super, super fast and customized for more. So we're now sort of hitting a next level of implementation decisions, like assuming we, in a month or two, actually get the fast meta compiler, and it seems it's very close, and we'll talk about that later. There's a couple options. One is just implement stuff in meta and let it run on that fast meta compiler. Another is go the next step and take your algorithm and heavily customize it to run really, really efficiently in like more level assembly language, so to speak, right? And on the other hand, these are like high-class questions to be worrying about, right? Because a few years ago, we were worrying about like, do we even have any idea how to implement any of this shit in a scalable way? Or will it just be, 10,000 times slower than neural nets still after the singularity, right? So we're definitely on to the next level of challenging choices about scalable implementation, which is really.
I want to pause there. I've got a couple of thoughts bubbling around in my head that probably need just a little bit of explanation to make sense. But I'll let you help fill in some of that explanation, Piyush. It's in the concept of meta as fast, scalable rewrite rules on a graph database. I want to try and make a relation to that, which has had all this performance work on it, in the way that we're doing what in essence can be thought of as a graph database query, or to some limited extent a rewrite using a different set of tools. And help me kind of bring this explanation, if you would, back into the realm of somebody without some of the background thinking about it. In a project that we're working on with Insurgent AI, we have a graph database underlying queries of a large set of ingested textual material. And the way that we're going about that is through a query optimization engine out of Stanford called DSPY, that is a prompt templating engine in essence. And the combination of this prompt templating engine and Cypher queries, which is you can think of as basically an SQL-like query language for graph databases, we're able to pull out the data in response to a user query out of that knowledge base and do something with it. And the something with it in our case is usually answer an explicit user question, but that's a rewrite of the relations in the graph database to the context of the user asking the question. And it seems like there is a very, very rough parallel with that process to the rewrite rules from Meta. Do you see it that way? Are you understanding his description of Meta as having a relation to what we've been working on?
Yeah, I mean, on a high level, I mean, he mentioned like a graph structure that's pretty similar to us. They're using tri-trees, also called prefix trees. And that's a topic that I just recently learned about. So I found that pretty cool. But could you explain like on a really high level for viewers who might not have that background, like what this fundamentally does and like its parallel to insurgent AI systems?
Yeah, sure. So, I'm not certain that there's an exact parallel there in all the areas, because what I think Meta is doing is allowing for these layers of rewrites to simulate cognitive architectures, and when you go into these multiple layers, this is probably where a lot of the performance pieces are coming from. But I'm trying to make the analog to what we're doing as kind of a one-layer rewrite rule, and let's say you've ingested a document into the graph database. And it doesn't really matter what that document is at the moment. I mean, perhaps our Mobius paper gets ingested. To go into that graph database, you're extracting triples. These are subject, object, predicate triples. Tom stabs Sue, a subject, object, and an action between the two. And the nodes go into the graph from your subject and object, and the predicate forms an edge on that graph. And when somebody asks a question of the graph, what crimes happened last night? This plainly didn't come from our Mobius paper. I changed domains as we're talking about. It's not going to do a control F word match with anything that's in that document. You need to prompt that appropriately to pull the data out of the document. And that's where the templated query comes from. You have this DSPY engine that provides the optimized prompt templates to help with that translation between the user language and the way that we're generating the cipher query that looks for all of the nodes and relations within the graph database to come out and then formulate an answer to that problem. And so that's essentially a graph rewrite of the knowledge that's in the knowledge graph being rewritten with the benefit of the context through the prompting in a way that the user understands as an answer to their question.
That's very interesting. Do you think that this architecture Meta could have implications for the continually learning aspect of AIs, AGIs?
Yeah, and that's where I think the definition of rewrites that Ben's talking about probably goes a lot deeper than just our questioning answer single layer rewrite, and really comes into the way that you and I, as we're processing information, even like a talk like this, the way that we're doing it is tying back to other things that we know and rewriting those things that we know combined with what we're hearing right now into a new set of derivative knowledge that's really the union of the set of things you already knew and were thinking about as the talk was going on, and the words that Ben is saying. Then when you go home and think about this, you're just kind of sitting over your lunch and pondering the talk and our discussion. You're again rewriting, and that rewrite is the rewrite of what you knew before combined with the rewrite of Ben's information into this little time-dependent nugget of information that you then think about and cogitate upon, and rewrites again and stores in a different way. One of kind of the wonders of the human brain, I think, is this ability to hold related thoughts and related paths through the database, as it were, in close proximity to each other, so that you're able to have the facility with all these previous iterations of thought. Probably why, as you're thinking about something that you've thought about 1,000 times before and really kind of gone deep on, you've got such richer knowledge representations than something that hasn't undergone that level of rewrite processes.
Yeah, that's a great point. And sort of continuing that analog to knowledge graphs, I wanted to like ask you, like I never mind. I think I'll ask you like after we watch a couple more minutes. I think it'll make a little bit more sense there.
Sure, sounds good. Let's jump back into.
Yeah.
Really quite interesting. The final element to mention implementation layer wise is the distributed aspect. So there's something called the distributed Atomspace being built by Andre Sena's team out of Brazil, which is a scheme for letting large Atomspaces be split up and distributed across a bunch of different machines, and that's making progress. There's a bunch of funky stuff in there that's being prototyped now. For example, if you need to match a pattern against a large atom space, you can do some sort of reasoning in the distributed atom space's query layer to split up into sub queries that will be executed against parts of the large atom space that's stored in different machines. Then there's a decentralized infrastructure, which is part of Greg Meredith's Firefly / Metacycle / ASI chain work, where you can take different atom spaces living in different processes or on different machines, and you can compile the meta language into Golang, which is a sort of blockchain smart contract language. Then you can use those Golang smart contracts resulting from meta compilation to coordinate together different atom spaces on different machines, right? So that,
If we could pause briefly here.
Yeah, totally.
Yeah,
We
I
brought in a
recalled
lot
what I
of
was
new stuff
about.
there.
Yeah. I kind of recalled what I wanted to say there earlier. So you mentioned that like when we learn new things, as we're talking right now, there's like sort of this one first pass that goes on, right? Where we root like new knowledge on top of existing knowledge, correct?
Yep.
But then later on, like as you said, while eating lunch or something, we sort of consolidate that knowledge. And I feel like in that first pass, stability appears to be roughly preserved, right? So I mean stability where we were talking about stability from the context of insurgent. For the viewer's context, this would be where you're creating a knowledge graph from one document, and you want to preserve the nodes and the edges in a rough state when you add another document, more data to it, and that's called preserving stability. However, that stability doesn't seem to be very preserved in that second round, at least locally, near where the new knowledge is being added.
Yeah, that's really interesting, and has me thinking about an even further extension of that. Stability is certainly not conserved. One of the reasons we sleep is apparently memory consolidation, and sleeping and dreaming about this talk is certainly going to be a less stable representation of the knowledge in that talk, but apparently forms some vital purpose in cementing that day's knowledge and thinking about things into a stable neurocognitive architecture.
Yeah, very interesting. Yep.
Yeah. He said a couple other things that we probably ought to pop into since we've broken things up a little bit in here. He's now on a path of a distributed architecture for cognition, which is super interesting from the perspective that humans have this inbuilt limit at what we can synthesize that stops at our ears, and that one computational unit being one brain sets these kind of upper limits that we haven't hit yet, but that we're still really aware of every day as to how much new information we can accommodate and process and work into a model. What Ben's talking about in setting the processing of integrative knowledge architectures on a distributed platform gets fully away from that, and talking about the blockchain aspects of this as being the ledger for accounting for the units of work in this distributed architecture, and possibly also the units of intellectual property ownership or participation in a project is an interesting mixture of an AI world and a blockchain world into a distributed architecture for thinking.
Yeah, that's very interesting. I'm not entirely familiar with the link between blockchain and AI, and I haven't really heard of that before. So this is very interesting.
Yeah, let's let him keep talking about it.
Yeah.
Meta to row compiler is there now and is being ongoingly improved, but this means you can run atom spaces distributed and decentralized, right out of the box, which again has been a lot of infrastructure work because we wanted, like, assuming we do make a breakthrough to AGI with all this, right? we wanted it to be immediately possible to run this on a decentralized network, as well as on a big centralized server farm, if that's what you want to do. So all that is the infrastructure. You can use that infrastructure actually for a lot of different things. I mean, you can implement NARS on that. And in fact, it's been done. We do have an implementation of NARS on that, thanks to Patrick and Peter, who just walked in. You can implement neural nets on that. And we've been exploring some ways in which it may be very valuable to do that. Like if you take a wavelet CNN or a waveformer, a neural net with a sort of hierarchical structure built into it, that maps very neatly into the more prefix-free infrastructure. Then you have, so for certain types of neural net architecture, I mean, the more infrastructure we have underlying the Atomspace now might be the most efficient way to do it, as well as a really transparent and easily manipulable way to do it. On the other hand, I don't personally think either of those is the best way to AGI, although they might be cool ways to AGI. As I said in my introductory remarks earlier, there may be a lot of different ways to get to AGI, right? But the route to AGI I'm most optimistic about is the Primus architecture, which most folks in this room have heard me talk about before, so I won't say a huge amount about it, but we'll highlight a bit the new elements there maybe before going on to whatever comes next. So that in terms of the Atomspace, Primus uses the Atomspace to store a variety of different types of memory, and you can look at it by enumerating the key types of memory in the human mind, like declarative memory, procedural memory, episodic memory, sensory memory, sort of action or motoric memory, memory regarding goals. We then associate appropriate learning and reasoning mechanisms with each type of memory. So we do explicit logic with declarative knowledge. We do evolutionary program learning or different sorts of reinforcement learning with procedural knowledge. For attentional knowledge, we do different sorts of activation spreading type things to spread attention through a network. For declarative knowledge, we also have concept formation algorithms like concept blending or fuzzy formal concept analysis. So you're taking a variety of different learning and reasoning algorithms associated with a number of different types of memory, and you're getting them all to work in this same big Atomspace metagraph. And the reason to do it in this tightly integrated way, rather than putting your different cognitive algorithms in different sort of black boxes with cables between them, the reason to implement the different types of memory associated with the human mind and learning and reasoning mechanisms associated with each of those types of memory, the reason to implement all these in the same big Atomspace metagraph is because of what I call cognitive synergy, which crudely means if you have different AI processes trying to help the same AI system, but by doing different kinds of thinking or different types of knowledge, you want all these different AI processes to be able to share intermediate state. So if one of them gets stuck, the others can help it out. So if one of them needs acceleration, the others can help it accelerate. I mean, sort of on the principle that working closely together and sharing as you go along is more efficient than having just different AI agents operating in black boxes and sharing only end results. So if you want to get that cognitive synergy where different AI methods doing different sorts of things with the common goal of making the same organism, you know, survive and flourish and individuate, self-transform, I mean, then you need a common meta-representational fabric for all of these different AI methods, and that's what Hyperon infrastructure and Atomspace provides. And within this overall framework, it then devolves into a whole bunch of detail, right? So we have the PLN logic framework running within Atomspace. We have Moses as an evolutionary program learning framework. We have ECAN as an attention allocation framework, and a whole bunch of other things. In terms of high-level control, I'll talk about that a little later when we get to the motivation system. But in terms of high-level control, you can sort of divide it into ambient self-organization activity versus goal-directed activity. And I think they're both important. I mean, you could implement just a big self-organizing network and try to coax general intelligence to crystallize out of it. I think that could work and is really cool. I don't think it will be the most efficient way to get there. I think having explicit goals on different timescales, having the system trying to use is assemblative AI methods to achieve these goals, given the observed context, is just the more efficient way to get shit done, which is why the human brain has that aspect to it also. It just shouldn't.
I'm going to pause there because a whole lot was just said that I think needs to be unpacked a little bit from that. And have to admit that without digging deeper into Hyperon, I don't know that I'm interpreting this this properly. But some of the things I want to see if match your interpretation here, though, Piyush. He was talking about the different forms of memory that Hyperon is allowing unified access to: episodic memory, semantic memory, declarative memory, all of these different types of memory in a human system share some elements of the same processing space, but also have other elements that seem not to be as fully shared. And so there are kind of these specialized blocks for some of those aspects of memory and cognition. Certainly, as you get into specified things like visual cognition and auditory language processing, you get different areas of the brain that light up in imaging studies that are more focused on that. And so I think that's kind of what he was getting at in those last statements of you could think of it as being one undifferentiated block of stuff that everything runs through, and you could get AGI out of that. But that he doesn't necessarily think that's the most efficient way of doing it. So there's absolutely a nod to the specialized computing structures over top of the memory, but also seems like he's saying that Hyperon provides a common generalized memory framework to hold all of the processing for these different uses. Was that a rough approximation of how you understood that section?
Yeah, for sure. I think that's an interesting take on it. Another thing that I took from this section is he was talking a little bit about reasoning, and he mentioned like models should not reason individually, like various boxes should not reason individually and come together at the end to figure out what the final result should be, but rather work together while they're reasoning. And I think that this is something we can kind of maybe see in the near term with large language models, because with things like we have swarms right now, and GPT-5 Pro and O3 Pro are rumored to be swarms where they have like 10 instances of GPT-5 running, and then they come together at the end and synthesize the answer. Instead of doing that, I think it would be very cool to see them work together while reasoning.
Yeah, that's really interesting. Yeah, that's an interesting take on that. And it makes sense in the human processing system. I mean, even if we think about our episodic memory or emotional processing kind of uses of the brain, and if I am thinking about a really deep technical problem that I'm really enjoying and I've been thinking a lot about, and then I get in a fight with my partner and go back and sit down about my technical problem, I'm going to pop away from my technical problem and be thinking about that argument and swapping back to the technical problem and trying to push myself into it. And it's plain the brain is doing both of those tasks within the same processing architecture, and that they interact with each other. And when we talk about a mixture of experts model, there is no interaction until that final integration step. And so they're really not functioning as a single unit.
Yeah, that's right. That's interesting. And I mean, like in the near term, do you think that like existing LLM architectures could be adapted to meet those specifications?
I don't know that it's entirely possible with the existing architectures, or desirable actually, and that one of the things that we at least are starting to get to with existing LLMs is some idea of explainability in processes. And the more we mix into that processing, the less explainability we have. In part, that's the magic of human thinking. That if I am on a walk thinking about my hard math problem and see a butterfly land on a bush and it bends just the way I was thinking about my math problem, there's this flash of insight, and I go, oh, wow, physics and butterflies and math problem, and out pops the answer. And that flash of intuition is coming from a fundamentally non-attributable process. But that fundamentally non-attributable process is also not explainable. And we're starting to see all of these regulatory elements around AI that we must be able to describe why an answer was arrived at. I think these may be incompatible goals to have complete explainability and a deeper integration.
Yeah, definitely. I mean, this talk so far seems to be very abstracted, like you mentioned in the beginning.
Mm-hmm.
And I know that he mentioned that their compiler architecture is going to be finished in maybe like 6 weeks. So I'd be very interested in having maybe a second podcast episode to talk about the code and how it works.
Yeah, I think the fact that we're getting this super high level overview is the fact that he was pushing 3 or 4 days of talks into a 15-minute overview. So we're definitely getting the sampler. Let's let him keep sampling for a couple more minutes.
Yep.
Shouldn't be dominant. Like you don't want to be 100% like reinforcement learning or goal achieving machine. You want to be that to a certain extent, and then let the spontaneous, unsupervised, self-organizing stuff roll in your unconscious to a certain extent also, right? And we have both of these aspects, and they can both leverage the same cognitive mechanisms to a significant degree. So where we're at now with the project, to wrap up on it, where we're at now, we have a lot of the scalable infrastructure working. We have Morph working, we have meta language interpreter, we should be launching within the next couple months scalable general meta interpreter, as well as the first version of this decentralized infrastructure, the ASI chain. We have the distributed Atomspace in a sort of alpha version where you can run it and play with it. The interfacing is being worked on. So the infrastructure is coming together quite nicely. And we're now at the point where we're taking the core cognitive algorithms, PLN, Moses, concept formation, ECAN, and we have simple meta implementations of all of these already existing. We're running at a very small scale because the meta interpreter so far has only let you do things in a small scale. So during the next 6 months or so, we'll be experimenting with these core cognitive algorithms at a large scale for the first time. And that's quite exciting, right? And it's hard to say exactly how fast things proceed there. I mean, you could have some things where the first time you run them on a really large Atomspace and a lot of data, they start to do something awesome, which you didn't imagine they would do. You may have other cases where the first time you run something on a lot of data, you find the whole algorithm was a piece of shit, and yet you have to go back to foundations and rebuild a better approach as fast as you can, right? You may find some things when you let them interoperate together at scale for the first time, they synergize and help each other and accelerate each other. You may find other cases where one algorithm didn't, in practice, help the other algorithm or understand its internal representations as much as you thought it would. So there's certain to be a lot of learning to happen, but it's a kind of learning we weren't able to do because we didn't have a scalable underpinning. And it's really similar in my mind to what's happened with deep neural nets in the last decade or so, right? Because I mean the path from LSTM to transformers, or from early CNNs to modern computer vision systems, is not that big in architecture design space, really. I mean, they're not to downplay the advance of people who invented transformers. I mean, it's all cool, but it's not, I mean, it's not that huge a leap from LSTM, as Jürgen Schmidhuber has told us many times. And I mean, that as Jan LeCun has told us, the step from early CNNs to mono-computer vision systems is not that big either, right? I mean, to make these modest advances in design space, you just need to be able to run a lot of scalable experiments so that will work and one didn't, and then go back and think and adjust, right? So I think we're about to start that phase for the Hyperon system where we can run scalable experiments and then figure out what variations of the architectures and algorithms and representations that seem to make sense, figure out what variations of those actually work really well, which is a sort of one you can only do in an iteration between scalable implementation and theory, right? So that's a quite exciting time to be at. Of course, it's an unpredictable process. My gut sense is it's not going to take 10 years. I mean, for what it's worth, I mean, my gut sense is we may be 1, 2, 3 years from huge breakthrough toward human level AGI. And when I first started work, I've told this story before, but it keeps getting more and more poignant, right? When I first started working with Nil on AGI oriented reasoning, it was right around when we launched the first version of OpenCloud, 2008, I guess. And Nil said, well, I think it's going to take us about 20 years to get to an AGI. And I'm like, I hope it doesn't take that long, but if it does, I'll probably still be alive then. So I mean, it's not that bad for it. So it's been a fun 17 years since that time. Not, and I think now he was about right. I mean, that seems like a reasonable time frame. And, so I think Neil should be the new Ray Kurzweil. We should not nominate him to predict all our timelines. So, until we have his digital twin, which will be even better. Yeah. So yeah. All that said, I know we're running super late, but let us move on to whatever is next in the agenda.
Let's pause there then. That was a good wrap up. And there was one thing at the last part of that I really hits me pretty hard. We've been talking about in the AI space emergent properties from large language models and how when you add parameters, they get better and better at thinking. What Ben is talking here about is not that. Ben is talking here about the addition of symbolic representations for enduring knowledge stores that are separate from a LLM-based knowledge store and that have a lot more large-scale integrative capacity than even a largest LLM that we have to throw at things. And I've been really skeptical at the claims of scale alone bringing us to AGI and the concept of LLMs. Yeah, we absolutely see different properties emerging from a few billion parameter model or a couple 100 billion parameter model than we do in a few million parameter model. Plainly, there are step changes in functionality and the ability to process as you within an LLM add size to the mix, but it's never seemed like it would actually make that leap to being able to handle some of the longer term goal setting and the longer term knowledge integration and stability questions and some of these other uses of AGI that come out of the deeper structure in Bin's scale up experiments here. So it's an interesting counterpoint to simply increasing parameter count.
Yeah, it certainly is different. And he mentioned that they started work in 2008, and it'd be really interesting to look at some of their ideas from 2008 and see how they've evolved. And one of the things I was curious about is like how will we as a user interact with the systems that they've built? Is it through text, or is it just like a knowledge storage device? Or like how does that work? And if it's text, like an LLM, How does it differ from an LLM like experience?
Yeah, yeah, no, I think those are all interesting questions. One of the things that I find really neat about what stayed the same, he mentioned a term that he didn't really ever define, probably because it's so central to his thinking now that it doesn't need definition anymore. But the atom space,
I was gonna
and
ask you about that. Yeah.
yeah, yeah. So essentially, I understand atom space as being a graph database. That it's a knowledge graph in much the same way that we're building knowledge graphs, but with the core concepts in that knowledge graph being really kind of refined and processed to the point that a node on the graph is a concept, and when we're building knowledge graphs in the insurgent AI pieces, we're really not doing that yet. We're taking text and a cat and kitten might get pulled out into separate nodes, whereas in a more refined knowledge representation, those might be merged into to a cat node with different flavors of cat being represented in it, and so these ideas of concepts as nodes rather than individual
Hmm.
words as nodes is something that we're currently struggling with in terms of the generalizability of our models. But aside from that kind of level of representation, I really see the atom space as being very much a jest. At this point, it's jest because we have implementations like Apache AGE and Neo4j and the like to render these concepts operable. But back in 2008, when the atom space was first kind of making its way into open cob concepts and thinking about knowledge representation, that tooling didn't really exist, and so it was definitely more of a leap to think of knowledge graphs as forming an underlying basis for AGI systems than it really is today.
Yeah. I mean, like one of the things we're exploring currently is concept graphs, and you mentioned like not being able to differentiate between kitten and cat, and concept graphs is like one idea that could potentially solve that. Taking a top-down approach rather than a bottom-up approach. Um,
But these are
and what?
rewrite rules in Ben's language. These are rewrite rules.
Yeah, pretty much. Just doing and scaling that should theoretically reach AGI, right?
Mhm.
Um, and you mentioned like just a couple of conversation turns ago that LLMs like usually learn and get better by using having more parameters, right? Um, it's interesting to note that GPT-5, although it is more capable than the 4 architecture, it actually has less parameters, at least it's rumored to. And
Mhm.
that's what gives it its speed. And I'm curious to see, I haven't really read up on it, but I'm really curious to see what they've done to enable that improvement without increasing parameter count.
Yeah, it's really interesting. I'm also really following closely the work on small models, and there's a bunch of people recently showing that a within domain trained small model can
Yeah,
equal or exceed the performance of a generalized large
like
model.
Quen 0.6b.
Yeah, exactly, exactly. Yeah, and when you think about having all of your knowledge in a system in a graph structure like the atom space, you can also begin thinking about the processing elements for portions of that graph being specialized, and that might actually be nothing more than domain-specific LLMs to operate on different sections of your atom space.
Yeah, for sure. Yeah. I mean, I've noticed that in my experience and use of smaller local LLMs versus the larger ones too. Yeah,
Hmm.
definitely.
Hmm.
Because like the larger ones have more real world knowledge of like all of the broad knowledge areas, domains. Um, but the smaller ones like they can still like talk, right? And they can still
Yeah.
execute actions. They just don't know as much, right? And if you're able to fine tune those smaller LLMs on one specific task, in the management and execution of knowledge graphs, for example, um, that could have huge potential for accuracy, right?
Yeah, yeah, it's interesting to think about this in terms of levels of
Mhm.
processing. That if I'm thinking really deeply about cats, I might just need a small model that is very specifically cat domain trained. But if I think about cats doing math, probably my cat model doesn't hold it anymore, and I need a different level of processing to do that integrative thinking between different
Exactly.
domains.
Yep. Yep.
Yeah. My cat only does math when supper time comes around, and the math is
Yeah.
impeccable.
Yeah, that's funny.
Yeah. Well, that was a really neat talk. As I mentioned at the start, really kind of abstract and high level, and didn't delve down into the details. I'm sure that's what the rest of the workshop's going to do some of. But yeah, it'd be really interesting to keep touching base on this as it grows and develops.
Yeah, well, I certainly will be watching the rest of the talk series later tonight. So yeah, thanks for sending me the podcast last night. And yeah, let's keep in touch about this podcast series.
Yeah, let's do. And thanks everyone in the PCCA podcast audience. We'll have more of these soon and delve down deeper into some of these topics. I appreciate you carrying along on the journey.
Awesome.
Bye-bye.